Hello, my name is Tyler Noxon, and I am a third-year mechanical engineering student here at Cal Poly.
And my name is Alex Joannis, and I'm a fourth-year chemistry student. Today we'll be taking a look at problem number 6 from chapter 12 of the General Chemistry Workbook. So before we get started, let's read through the entire problem to sort of get a general understanding of what it is exactly that we're being asked. So we can take a look at the beginning of part 6, and it says we should draw a rough sketch of a potential energy profile for each of the following cases, labeling delta G standard for the reaction, the activation energy, the reactants, the transition states, and the product. For part A, delta G for the reaction, delta G standard for the reaction, should be positive 10 kilojoules per mole, where the activation energy should be 25 kilojoules per mole, and for B, delta G standard should be negative 20 kilojoules per mole, and the activation energy should be 50 kilojoules per mole. And for parts C through F, we'll read those a little bit later once we get to them.
It seems like we're being asked to draw a number of curves all on a single potential energy diagram, so that's just what we're going to do. Before we can actually get to drawing any potential energy curves, however, we'll need a graph with the proper axes. You may be asking yourself, what's the point of a graph like this? Or what are the units on these axes? Well, let's break down exactly what this kind of graph is useful for and what it can tell us before going any further with problem 6. In potential energy profiles, the x-axis is something we typically call the reaction coordinate. What does this mean? Well, you can sort of think of it as the reaction progress. The further we go to the right on the reaction coordinate, the further the reaction is to forming the end products. The free energy condition of the reactants will be drawn on the left, and the free energy conditions of the products will be drawn on the right. So what about the y-axis? That one is a lot less abstract. It's the standard free energy of either the products or reactants. If we have more than one product, their free energy is the sum of each product's free energy. The same applies to reactants as well.
Now that we've got all that straight, we can take a look at part A. Here we're told that our change in standard free energy, or delta G standard, is positive 10 kilojoules per mole, and our activation energy, or E sub A, is 25 kilojoules per mole. Based on the discussion we just had about the axes, try plotting the positions of the products and reactants in this case. Here's a hint before you get started. The actual free energies of the products and reactants don't really matter in this case, only the difference between them. Resume the video when you think you're ready. So, your graph should look a little bit something like this at this point. Now, we have the reactants and the products in the right place relative to each other, but what about the other term, the activation energy? Well, what that tells us is the difference in energy between the reactants and what we call the transition state. And the transition state exists for a very brief amount of time in between the products and reactants. Take another moment and draw a point on your diagram where you think the transition state should exist. Your diagram should now look a little bit something like this. The transition state always exists between the reactants and the products. The last step in completing your rough sketch is to connect all of the dots. Now you have a complete energy profile for this theoretical reaction. Using what you learned solving part A, try sketching the profile described in part B.
Your diagram for part B should look something like this. One thing worth noting is that even though the products are lower in energy than the reactants, the transition state will still need to be the highest point on your diagram. This is because the transition state is always the most energetic species in any single-step reaction. Part C asks us to draw a catalyzed reaction pathway for this energy profile. Catalysts are molecules which stabilize the transition states, bring them down to lower energies. So, in the case of part A's profile, all we would do is plot the activation energy lower on the y-axis, but not too low that we don't have a peak anymore. No matter how effective your catalyst is, you can't eliminate the transition state. So we would draw the catalyzed path like this. Pause the video and try drawing the catalyzed reaction pathway for part B. It should look something like this.
Now let's discuss part E. It asks, how does the catalyst affect the equilibrium concentration of the reactants and products? Based on what you know about reaction kinetics and equilibrium, do you think a catalyst will affect the equilibrium concentrations? Well, as a matter of fact, the equilibrium concentrations won't change at all. Now let's think about why that is for a second. What are we actually changing when we add a catalyst? The free energy of the reactants and products aren't changing at all. All that's changing is the activation energy, the energy required for the reaction to actually occur. All we're doing by adding a catalyst is making it easier for the reaction to occur. The products need to stockpile less energy before the reaction can actually progress. The reaction will occur more quickly, but not more completely.
This leads us to part F. Does the catalyst have an effect on the reverse reaction rate? If so, what is the effect? The catalyst affects the reverse reaction in the same way as the forward reaction. As we can see, the activation energy for both the forward and reverse reactions have been lowered. We can also think about this in terms of our answers to part E. Because the forward reaction rate increases, the reverse reaction rate must also increase in order for the equilibrium position to stay the same. Thanks for watching our video. Hopefully now you have a better understanding of potential energy profiles and how to read and generate them.